Okay, this is the pre-class lecture for October 24th. So when we talked about SN2 reactions for Monday's pre-class lecture, we saw that there was a nucleophile, there was a leaving group, and that it was a concerted one-step mechanism, that primaries reacted faster than secondaries, but tertiary didn't react at all, and I'll come back to that later because we'll talk about a different mechanism. But just to finish up the idea of SN2, there's two things that we should look at. And the first is what's called nucleophilicity. And that's basically the strength of a nucleophile. Are there different factors that go into making a good nucleophile or a poor nucleophile? And how do we classify nucleophiles? And then also, how do we look at leaving group ability? So what makes a quote-unquote good leaving group, what makes a poor leaving group, and what factors go into that as well. And then the other thing that we'll talk about after we talk about SN1 and SN2 reactions is the idea of how the solvent can play a role. But we won't do that yet until we introduce the idea of SN1, which I will do in a few minutes. So let's talk about leaving group ability first. So when your nucleophile comes in and attacks your carbon or donates a pair of electrons to this carbon, and the leaving group leaves, we end up forming our substitution product with inversion of configuration if this was a chiral center to begin with, and then we end up with our leaving group, anion. So how would the ability of the leaving group to leave, whether it's a good leaving group or a poor leaving group, how would that play a role in the rate of the reaction? So if I said, will a quote-unquote good leaving group speed up or slow down an SN2 reaction, what would you say? Well, if you said that a good leaving group will cause an SN2 reaction to occur faster, you're right. Because the better the leaving group, the easier it is for the nucleophile to kick it out. And the poorer the leaving group, the slower the SN2 reaction, it's possible that the leaving group won't leave, and therefore the molecule can't undergo SN2. So what factor goes into leaving group ability? And I'm starting with leaving group ability because there's simply one factor that goes into making a good leaving group, and that is the idea of the basicity. So the basicity of the leaving group, in other words, when it's over here, what kind of base is it, plays an important role, and the basicity is then inversely related to leaving group ability. And what that means is that when you have a strong base, you have a poor leaving group, and when you have a weak base, or if you remember back, I introduced the idea that something really can act not as a base at all, that gives you a good leaving group. So leaving group ability is only based on one thing, basicity, and it's inversely related to the basicity. So now what we have to do is we have to go back to our little periodic table, and the important part of the periodic table where all of these elements that we use are, and we have to think about, well, how does basicity, what's the trend going across and down the periodic table in terms of leaving group ability? So if you don't remember that, basically a C minus, N minus, O minus, and F minus, basicity increases. So basicity increases as we go from right to left across the periodic table. So F minus is a weaker base than C minus. And C minus is a stronger base than N and O and F. Going from top to bottom, how does basicity change? Well, it turns out that basicity, as we go down the periodic table, well, I shouldn't confuse the arrows. Basicity will increase as we go up the periodic table. So as we go up from iodine to fluorine, there your basicity increases from bottom to top. So F minus then is a stronger base than Cl, which is stronger than Br, which is stronger than I. So therefore, if we're looking at leaving group ability, things that would make good leaving groups are first of all things like Cl, Br, iodine, and the poor leaving groups are going to be the things that are the stronger bases, which to some extent are going to be fluorine, oxygen, nitrogen, carbon, and I'll throw in hydrogen in there as well. And I'll even go so far as to say this, that in terms of leaving group ability, some of these atoms do not ever leave on their own. So for instance, if I want to look at the next page, if I have, for instance, a carbon, let's say I've got CH3 attached to a chlorine. Well, that's an okay leaving group, or it's a good leaving group is what I would call it. And so this being a good leaving group will leave. But on the other hand, if I have an OH group attached, OH minus is a stronger base than Cl minus, and so OH is a poor leaving group. And I'll even put restrictions on it that says OH won't leave unless protonated. And I'll come back to that issue of protonation either at the end of the lecture today or for Friday's lecture. So things that won't leave, OH will not leave unless you protonate it. The same thing would be true for a nitrogen-based group. These two won't leave unless they're protonated. Chlorine is okay, bromine is okay, I would even say that fluorine is okay as a leaving group. They will leave. But oxygen and nitrogen are going to have to be protonated before they will leave. Now things that never leave are hydrogen and carbon. Those never act as leaving groups. And this kind of makes sense because in the design of organic chemistry, we normally use the carbon-carbon bonds as our skeletons. And the carbon-hydrogen skeleton then has functional groups hung off of it to make the different kinds of molecules that we have. Well, a carbon-hydrogen skeleton wouldn't be a skeleton if you could displace carbon atoms from it. And so carbons and hydrogens never act as leaving groups. So we will never have a nucleophile come in. Some nucleophile will never come in and kick off a hydrogen or a carbon. But this nucleophile could come in and kick off a chlorine, bromine, or fluorine very easily. And that nucleophile could also come in and kick off an OH or an NH2 if that group is protonated first. Okay, so that's the idea of leaving groups. We have good leaving groups, we have poor that are going to need some help by protonation. And then we have groups, the strongest bases, your carbons and your hydrogen, that never act as leaving groups. Okay, so leaving group is based on one thing, basicity. So what about then the strength of the nucleophile? So how do we judge nucleophile strength? Well, it turns out that there's three factors that go into judging the strength of a nucleophile. Number one is charge. And so a negative nucleophile, a negatively charged nucleophile, is going to be stronger than a neutral nucleophile. So much so that I will call a negatively charged nucleophile strong, and I will call the neutral nucleophile weak. So what kinds of strong nucleophiles are we talking about? Well, we could be talking about Cl minus, Br minus, OH minus. We could be talking about an N minus, or we could even be talking about a C minus, or F minus, or I minus. So these are not in any particular order. I'm just kind of listing all of our nucleophiles that could be negatively charged. I suppose I would even throw in a Cn minus as a potential nucleophile. So all of these are strong nucleophiles because they have a negative charge. Now what are weak? So here are your examples of strong nucleophiles. What are your examples of weak nucleophiles? Well, the examples of weak nucleophiles are things like water, that has a lone pair so that it can function as a nucleophile, but it doesn't have a charge. So we're going to call water a weak nucleophile. The other weak nucleophiles are alcohols. So if you have like methanol as an example, this oxygen can act as a nucleophile because it's got a lone pair, but it does not have a negative charge, and so therefore it's not a strong nucleophile. We classify it as weak. And we'll see some examples here in the rest of the lecture where we can react weak nucleophiles as well as strong ones in the reactions. Now, I didn't talk about weak nucleophiles in the SN2 section because weak nucleophiles turn out they never undergo SN2. So weak nucleophiles only do SN1 reactions. Now, strong nucleophiles can do either SN1 or SN2. So they can do either one. Although I'll reclassify some of these really strong nucleophiles like the nitrogen and carbon. And you might say, how do you know they're really strong? Well, charge is the first thing. So a negative charge is stronger than a neutral. The second thing that we have is the idea of basicity. Okay. So I don't think I left gonna have to pull up a couple slides here because I'm running out of room. Okay. So when we talk about the second factor that goes into play, so in other words, if I'm comparing F minus and Cl minus, which one is the better nucleophile? Or if I compare Cl minus to OH minus, which one is the better nucleophile? They're both negatively charged, therefore that's a tie. So then we go to one of two things. The second factor is basicity, and the third factor is what is called polarizability. Now I talk about each one of these individually, but it turns out that they can be used, they're used in different circumstances. So let's say that in my number 2 is just going to be simply basicity. Well, we had our periodic table of carbon, nitrogen, oxygen, fluorine, chlorine, bromine and iodine. It turns out that basicity is the factor with the following: the stronger the base, the stronger it is as a nucleophile. So this is a direct relationship. It turns out that basicity only comes into play if I'm looking at a horizontal comparison from the periodic table. Okay, so if I was to compare O minus and F minus, so I compare something like hydroxide and fluoride. If that comparison is on a horizontal relationship, then the stronger base is the stronger nucleophile. And which one would that be here? Well, it would be hydroxide as a stronger base than fluoride, so hydroxide would turn out, in this case, to be the stronger nucleophile than fluoride. If I had a nitrogen negative ion, that would be even stronger. And the strongest nucleophiles that we can get are carbons that have negative charges on them. Okay, so this is sort of a horizontal relationship that we have. If I had in a second row, I could say that S was a stronger nucleophile than chloride because of the relationship, the horizontal relationship. So when you're comparing two things that are horizontal on the periodic table, basicity is what dictates which one is the stronger nucleophile. But what people found was that when they went and they determined the rate of the nucleophile, so in other words, if I have a nucleophile that is reacting with, let's say, CH3X to form the substitution product and the X minus leaving group, we could measure the rate of that reaction, and what they found was that when nucleophiles that were horizontally related on the periodic table were run, that the rate increased based on which one was the better, was the stronger base. But when they started to look at the vertical relationships here, what they found was that it was exactly the opposite, that it wasn't related to base. So in other words, when they ran, for instance, bromide versus iodide, they found that iodide was the better nucleophile. And it's the one that speeded up the reaction relative to bromide. So this vertical relationship then is opposite of basicity. And so therefore it uses what's called a term called polarizability. So polarizability comes into play when you have now vertical relationships. So for polarizability then, iodine would be the stronger nucleophile than bromine, than chlorine, than fluorine. If we put sulfur in, it's known that sulfur is a stronger nucleophile than oxygen. Phosphorus is a stronger nucleophile than nitrogen. So this vertical relationship then says that as you go down the periodic table, polarizability and then nucleophilicity increases. Okay, so as you go down the periodic table, the polarizability and the nucleophilicity increase. But what is polarizability? Well, polarizability is what I call squishiness. It's basically the ability that the ion has to deform. And when it deforms, it can therefore concentrate electron density. Well, if we were to take, for instance, a fluoride and an iodide and react it with something like CH3F, which one of these two would react faster? Well, now that we know that when we're comparing two nucleophiles that are vertically related on the periodic table, we have to consider polarizability. So I would be predicted to be the better nucleophile in this case. Why is that? Well, what do we know about size as you go down the periodic table? What happens to the size of the ion? Well, as you go down the periodic table, size increases, right? And so this idea of polarizability says that the bigger the ion, the more ability you have to deform the electron density and to concentrate it. And all of this comes about because of the mechanism of SN2. So if you remember, for the leaving group is attached to the carbon with an sp3 bond, and there's this little tiny overlap of that orbital that we see in that sp3 hybrid orbital. Well, remember, it's the nucleophile that's bringing its pair of electrons in another orbital and overlapping the little tiny orbital of the sp3. And that's actually how you get the SN2 reaction to occur. Well, the more the nucleophile can concentrate its electron density, so in other words, if it can concentrate that electron density, then what will happen is that you will get better orbital overlap. Between the nucleophile's orbital and the little tiny lobe of the sp3. And so if you can concentrate the electron density more, then you'll get better orbital overlap, and you'll get, in essence, a more stable transition state, which means you'll get a lower activation energy, which means you'll get a faster reaction, faster SN2 reaction. So iodine being very large, because on the periodic table, iodine has more electrons at a higher principal quantum number, and the electrons at higher principal quantum numbers are by definition farther away from the nucleus. They're less tightly held, and if you remember back to general chemistry, this term called shielding, where you've got all the inner core electrons then repelling the outer valence electrons. So the bigger the ion, the more likely you are to be able to then deform and put some extra delta minus charge as you were, if you're able to deform your clouds. And iodine's able to do that because those valence electrons aren't held to the nucleus as quickly, and so, or as tightly, so that you can really kind of squish the iodine ion and come up with an area of more concentrated charge. If you have a fluorine, fluorine is a very small ion, and because its valence electrons are much closer to the nucleus, they're held much more tightly. And so fluorine kind of is a golf ball compared to the iodine being a Nerf ball, which would be much more squishy. So iodine being more polarizable then is able to make a better overlap with the sp3 orbital of the carbon, and therefore undergoes SN2 much faster. Okay, so that's the idea of polarizability. So depending upon your relationship between your elements or between your ions for the nucleophile, if it's horizontal, you go on basicity. If it's vertical, you go on polarizability. So vertical, things to the left, ions to the left are stronger nucleophiles. Polarizability, things to the bottom of the periodic table as you go down, they become stronger nucleophiles, which I'll introduce this idea, but then I'll talk about it later on, leaves iodine in kind of a very weird spot, because iodine would be a good nucleophile based on polarizability, but iodine would also be an excellent leaving group if we look at the leaving group relationship, because going down the periodic table you get a better leaving group. So iodine is both a good nucleophile and also a good leaving group. And so what that means practically for the experiments are that if you take a nucleophile and you were to react it with an alkyl iodide, when the nucleophile came in and kicked off the iodide, you would end up with your substitution product, but you would also end up with I minus. So if I look at this reaction, I'm reacting a nucleophile with a molecule that's got a pretty good leaving group, but then once I form the iodide, it's a pretty good nucleophile that could come back and attack this carbon and reverse the process. And so for what this means practically is that when you react alkyl iodides, you sometimes get equilibria between the two different products. Okay, but this is how we judge nucleophilicity. Number one, charge, negative ions, strong nucleophiles, neutral, we call weak. After that, you have a horizontal relationship. You're going to make the relationship based on basicity, stronger base, stronger nucleophile. Going up and down on the periodic table, it's polarizability that determines which one is a better nucleophile, and so the polarizability, you've got then things at the top of the periodic table are not as strong in nucleophiles, things lower down because of the size and the ability to redistribute electrons to make a more concentrated orbital. Okay, so those terms of good nucleophile, poor nucleophile for negatively charged and neutral nucleophiles, as well as choosing the better base or the more polarizable atom, therefore getting at which nucleophile is stronger, we're going to use in the reactions that we talked about, and we'll probably talk about those for probably for Friday. So that's sort of the end of the SN2 stuff, but it will come into play, particularly neutral nucleophiles will come into play in a minute as we talk about SN1. So last time we talked about the relative rates of reactivities for alkyl halides. Primaries reacted the fastest in SN2, secondaries were second fastest, and it turned out that tertiary alkyl halides did not undergo SN2. And I just said they don't undergo SN2, and how do people know that they don't undergo SN2? Well, here's what happened. Let's say they took something like a hydroxide ion, pretty strong nucleophile that we just talked about, and they reacted it with tertiary butyl bromide. And what they found was that while they would get substitution product, when they measured the rate of this reaction, they got a completely different rate equation than what they got for SN2. Remember that for SN2, the rate equation is equal to the rate constant times the concentration of the nucleophile to the first power times the concentration of the alkyl halide to the first power. So it was second order overall, which made it bimolecular kinetics, and that's where the 2 in SN2 comes from. When they measured the rate using a tertiary halide, what they found was that when they doubled the concentration of the alkyl halide, the rate actually doubled. So it was first order in alkyl halide. But the interesting thing was that when they doubled the concentration of the nucleophile, and it wasn't just hydroxide, it was any nucleophile, they found out that the rate was unchanged. So they got no change in the rate of the reaction when they changed the concentration of hydroxide. Now, in kinetics, that means that it was 0 order in nucleophile. And, anything to the 0 power means 1. And so what they found was that the rate equation had changed and now become only dependent on the alkyl halide to the first power, and that the strength or the concentration of the nucleophile played no role in the reaction of a tertiary alkyl halide. And so what this means in chemistry is that when you have a change in rate equation, you have a change in the mechanism for that reaction. And we talked about the idea that if you were trying to take a nucleophile and do backside displacement on a tertiary alkyl halide, that the steric hindrance would cause the nucleophile not to be able to get close enough to the carbon to form the transition state. Or really technically what's more correct is to say that the transition state energy of trying to get the nucleophile close enough to form the trigonal bipyramidal geometry, that transition state was at such a high energy that the activation energy was too high for it to overcome. But either way, we said that nucleophiles don't do SN2 reactions with alkyl halides, but tertiary alkyl halides do undergo substitution, but by a different mechanism, and this is the rate equation for that other mechanism. And so that's where people started trying to figure out, okay, what is the mechanism by which a tertiary halide reacts? And here's the mechanism that was ultimately determined. So when you react a strong nucleophile, and that's a nucleophile with a negative charge like our hydroxide that we just used, what they found was that the first step of the mechanism involved breaking the carbon-bromine bond. And in this case, what would happen is that pair of electrons would go to the bromine, and the carbon then would be out an electron because the bromine took both of its electrons with it. Now, why would that happen? Because the carbon is slightly positive and the bromine slightly negative, so the electrons will go with the more electronegative element. When that happens, you end up with a carbon that now only is sharing 6 electrons and has a +1 formal charge, and then the bromide ion. Well, this carbon that has a positive charge is what's called a carbocation. And so a carbocation, or it's also called a carbonium ion. But carbocations or carboniums are unstable species because they only have 6 valence electrons. They look surprisingly similar to another intermediate that we encountered recently, a radical. But this is even worse because the carbon now has lost that unpaired electron of the radical carbon, so now it's got a full-blown positive charge. But that's what they found the first step of the mechanism, or that's what they proposed the first step of the mechanism to involve, is the breaking of the carbon leaving group bond to form the leaving group anion and a carbocation. And then in a second step, the nucleophile would come in and attack that carbocation. So in other words, the nucleophile with a negative charge has lone pairs that it can go ahead and use to form a carbon nucleophile bond. And so when it does that, the carbon gets back to sharing 8 electrons. The nucleophile, which had a negative charge, had an extra electron here, then loses ownership to the carbon, and we form a neutral molecule. And so that's how we get our substitution product. But this time we get it in 2 steps. So let me just rewrite that a little bit here. Let's say I'm going to write this as R3C and X for my leaving group. So I'm going to do this reaction for a tertiary alkyl halide, and I'm going to react it with my negatively charged nucleophile. I am going to get substitution. So step 1 of the mechanism, or what we would call in general chemistry elementary step 1, was to take this carbon halogen bond, break it. Now notice I'm using a two-headed or a full-headed arrow here, so both of the electrons in the bond are going to the halogen. Could we write the transition state for this step? Well, we're going to have a carbon-halogen bond partially breaking on its way to form that carbocation and that X minus. Now over here in our transition state, we have to put in the charges now. So carbon is on its way from having 0 formal charge to +1, therefore it's a delta plus. This halogen is on its way from 0 formal charge to -1, so it's going to be delta minus in the transition state. Okay, and then in elementary step 2, we're going to have this carbocation react then with our nucleophile with a negative charge. That nucleophile is going to donate the pair of electrons back to form the carbon nucleophile bond. What's that transition state going to look like? It's going to have a partial bond between the carbon and the nucleophile as it's going from no bond to forming a single bond. And in terms of charges, the carbon's going from +1 to a 0 formal charge, so it's delta plus. The nucleophile's going from -1 to a 0 formal charge, so it's delta minus. So here's my 2 transition states for those 2 elementary steps of the reaction. Now I have a question. What is the carbocation? What would we call the carbocation for this reaction? If you said that the carbocation is the intermediate, you're correct, because it's produced in one step of the mechanism, it's consumed in the second step, so therefore it doesn't show up in the overall reaction. Now, when you propose a mechanism that involves carbocations, somebody somewhere down the road had to prove the existence of a carbocation. And that was done in the probably 50s and 60s. And there were some strange carbocations that were looked at back in that time period. But one of the things that people then started to look at was they had to ask themselves, well, why is the kinetics of this reaction only based upon the alkyl halide concentration and not the nucleophile? Well, when you have a 2-step mechanism, you have to ask yourself which step is the fast step and which step is the slow step. And so in this case, it turned out that the slow step was the first step in the mechanism and the fast step was the second step in the mechanism. And how did they know that? Now, essentially, that's what kinetics told them. If you remember back in general chemistry, if I had a reaction of A plus B and it formed C in elementary step 1, and then C reacted with another molecule D to make, let's say, molecule E, so that my overall reaction here is A plus B plus D makes molecule E. When you have elementary steps, you're allowed to do something that you're normally not allowed to do in kinetics. Let me go back here to the overall reaction up here of this plus the nucleophile. So these two reactants. When I teach general chemistry, which isn't that often anymore, but when I do, I stress to people that when you're going to write the reaction, the overall rate equation for a reaction, that the overall rate equation has to come from experimental results. So the way that they determined the rate equation for this reaction was they doubled the concentration of alkyl halide and saw what happened to the rate. They doubled the concentration of nucleophile while keeping the alkyl halide concentration constant and saw what happened to the rate. Well, in this case, again, if they doubled the concentration here, they got 2 times the rate. When they doubled the concentration of the nucleophile, they had the rate stay the same. So our overall rate equation, in this case of K times the alkyl halide to the first power, that overall rate equation came from experimental data. But one of the things that you're allowed to do for elementary steps is you're allowed to write the rate equation using the stoichiometry of the reaction. You're never allowed to do that in the overall rate equation. For the overall rate equation, you are allowed to do that in equilibrium expressions, but in this case, if you were to have an elementary step, you are allowed to write the rate equation of that elementary step. So if I did that for A plus B, I would say that the rate is equal to a rate constant times the concentration of A times the concentration of B, each to the first power, because one molecule of A reacts with one molecule of B in elementary step 1. In elementary step 2, what would I have? I'd have the rate is equal to K times the concentration of C to the first power times the concentration of D to the first power. So the idea here is that you're allowed to write the rate equations for elementary steps, and in this case they're different. And so using these elementary step rate equations, let's say down here that the overall reaction rate was equal to K times concentration of A to the first power times concentration of B to the first power times the concentration of D to the 0 power. Well, when you write the rate equations of the elementary steps, the idea here is that whichever of the rate equation of the elementary steps most closely resembles the overall reaction rate expression, that is going to be the slow step of the reaction. So since the change in concentration of D did not play a role in the overall rate, what would happen is that this would be the slow step and this would be the fast step, so that the slow step, the overall rate of the reaction, is dependent on the rate of the first elementary step, or what we would call the rate determining step. So by the time that intermediate C is formed, as soon as it's formed, it immediately reacts with D to make the final product. So the rate is really the rate of forming the intermediate. The rate of the reaction is really the rate of forming the intermediate, since the intermediate reacts very quickly to form the final product. Well, the same thing could be set up here. If the overall rate equation, if your overall rate is equal to K times concentration of alkyl halide to the first power and the concentration of the nucleophile to the second power, what would be the rate equation for elementary step 1? It would be rate equals K times concentration of R3CX to the first power, because one molecule dissociates in that step. What would the rate equation be for step 2? Rate equals K times concentration of carbocation intermediate to the first power times concentration of nucleophile to the first power. Because one molecule of carbocation reacts with one molecule of nucleophile. So in this case, if step 2 was the rate determining step, the concentration of the nucleophile would show up in the overall rate equation. The fact that it doesn't is how we determine that step 1 is the slow step and step 2 is the fast step. So step 1 here is our rate determining step. Okay. And so from the kinetics, people determined or proposed the idea of this reaction. They proposed that this is a two-step mechanism where we have a carbocation intermediate, and that the first step, the formation of that carbocation intermediate, is our rate determining step. So the kinetics initially showed that the mechanism was different for tertiary halides, and then it also showed that there was a two-step mechanism with the alkyl halide forming the carbocation as the rate determining step. Okay. So we have a different mechanism. Come back to this carbocation in a minute. Well, I guess we'll come back to it right now. I made the analogy of the carbocation to a radical, except now that that unpaired electron has been removed, that carbon has a formal charge of +1. So the question is, what's more stable? A tertiary radical? A secondary radical? Or how about a primary radical? Or a primary carbocation? So which of these three carbocations is the most stable? Well, if the analogy to the radicals holds, then the tertiary carbocation must be the one that's the most stable. Why? Because we can make the same argument as we did for radicals, hyperconjugation. We could say that this carbon has some negative charge that it's pulled away from each of these three hydrogens, and then that carbon can donate some of that electron density to the carbon, which really needs it now because it's only got 6 valence electrons. So the more alkyl groups, the more hyperconjugation you get for donating the electron density, and therefore you get a more stable carbocation. In the case of the secondary one, you only have 2 groups that can do that, so it's going to be less stable. And in the case of a primary, we did write the structures of primary radicals because the alkyl group was able to provide enough electron density to make a radical stable. But the problem with the carbocation is it only has 6 valence electrons, so it's even more starved for electron density. One alkyl group isn't enough to do it. And so what we find is the primary radicals are very unstable, and I'll say in solution, because it turns out that in the gas phase, primary carbocations do form. And next semester in lab, you'll talk about mass spectrometry. And in mass spectrometry, you can actually see primary carbocations very easily. But that's a high energy environment. Solution isn't a high energy environment. So therefore, primary carbocations are very unstable in solution, and we are going to basically say that they do not form. Therefore, we do not write the structures of primary carbocations in our mechanisms. We're going to treat them as if they don't form. Now, primary radicals are perfectly fine. They're not stable, but we can write them. We never write the structures of primary carbocations in this class. So basically, you're up to rule number 3 of things you don't do in organic. Number 1, you don't take it. Number 2, you don't write 5 bonds to a carbon. Number 3, you don't write primary carbocations. Okay, so the tertiary carbocation is more stable than the secondary, and so primary carbocations now will not undergo SN1 reactions because they can't form the intermediate that's required in SN1. But that's okay because they react by SN2. Well, may not be okay in some cases. Now, let me just come back here and add one other thing. The rate determining step involves the reaction of one molecule. That means that the rate determining step is unimolecular. The kinetics of this reaction is first order overall and only depends on one molecule's concentration. That's where the SN1 now comes into play. This is now unimolecular nucleophilic substitution. So whereas SN2 is bimolecular, SN1 is unimolecular because of the rate determining step only having one molecule within it. Okay. So here's just a summary of that. The rate is K times concentration of alkyl halide. It's unimolecular. Therefore, the alkyl halide breaking apart is the slow step. That's the rate determining step. The nucleophile, the negative nucleophile reacting with the alkyl halide, or with the carbocation then, carbocation intermediate, is the fast step of the 2 elementary steps of the mechanism. Okay, so what do we know about SN1? Well, we know that it's a 2-step process, formation of the carbocation, and then the carbocation reacts with the nucleophile. So whereas SN2 is a concerted 1-step mechanism, SN1 is a 2-step process with a negative nucleophile, and the rate determining step is the formation of the carbocation. What does the reaction coordinate diagram look like then for an SN1 reaction? Well, it looks like this. We're going to have then the formation of an intermediate, which is again the valley on the curve. So we go through our transition state. Remember, our transition state here would be the partial carbon-bromine bond breaking with the delta plus on the carbon and the delta minus on the bromine. Over here, your transition state would be the partial carbon nucleophile bond forming, with the carbon again being slightly positive, the nucleophile being slightly negative. So the reaction coordinate diagram looks different for an SN1 reaction because now it has this intermediate. Okay. Now, one of the issues that we have when we talk about weak nucleophiles versus strong nucleophiles is this. Water is what kind of nucleophile? If you said weak, you're correct. Well, it turns out that weak nucleophiles can only undergo SN1, not SN2 reactions. So they can only undergo SN1. Water is not a strong enough nucleophile to displace the leaving group. So if this was a primary alkyl halide, if you tried to react it with water, you would get no reaction. But if you react water with a tertiary or a secondary halide, because secondary halides are stable, they form a stable carbocation, then you'll get SN1. So we could not react neutral nucleophiles, neutral nucleophiles that don't have a charge, weak nucleophiles. We can't react weak nucleophiles in SN2, but we can react them in SN1. But the question is, how does that reaction go? And look at our product. If we react water, HOH, with the alkyl halide, what we end up doing is we end up substituting the Br for an OH group and then making HBr. So the question is, how does that reaction occur? It's going to actually occur by 3 steps in the mechanism, not just 2. So this reaction is sometimes called solvolysis, because what happens is that if you use water, or you could do this reaction with an alcohol, and I'll write the mechanism out here in a minute or two. These are sometimes the solvents of the reaction, so you just drop the alkyl halide into the solvent and you get the SN1 to occur. So this is called solvolysis. That literally means cleavage of the solvent, which is exactly what we're doing. We're cleaving the solvent to form the substitution product, and then the H plus will go with the Br minus. Okay. So here's how this mechanism works. The first thing we do is we break the carbon-bromine bond. We go through our, and I'll put the transition state in here. Go through that transition state to form our carbocation intermediate. Then in the second step, the carbocation gets reacted with the whole neutral nucleophile. Okay. Now that whole neutral nucleophile does have lone pairs that can be donated to the carbon. Water does not break up into H plus and OH minus. Well, actually, that's not true, is it? Because in general chemistry, you learned that water was actually in equilibrium with H plus and OH minus. But then what was the equilibrium constant for this reaction? Might be stretching your general chem knowledge here, but the equilibrium constant is 10 to the minus 14th. Right? This is the autoionization equilibrium of water that gets you pH 7 and gets you all of the concentration of H plus and OH minus. But here's the key. The key is there's not much OH minus in solution, so we're going to treat the whole water molecule as a nucleophile. So don't do that. So we take this water, the lone pair now reacts with the carbocation so that now I form a carbon-oxygen bond. The oxygen now only has one lone pair, and here's a key thing. I reacted a +1 species with a neutral species, therefore my overall intermediate now has to have a +1 charge. Where's the +1 charge? Well, it's in the formal charge on this oxygen. Because now what happened was that the oxygen of the water donated its 2 electrons to the carbon, and the carbon now has taken official ownership of one of those 2 electrons. So now I end up with an oxygen with a +1 charge with a +1 formal charge. And this is now called an oxonium ion. A carbocation is also called a carbonium ion, but I don't use that term very much. So because the whole neutral nucleophile reacts with the carbocation, I now get a second intermediate. And then what happens? Well, then what happens is we cleave this OH bond, and let me go back here. We should probably write I should probably write the transition state for this reaction, since I've been doing that. The transition state here would have partial bond between the carbon and the oxygen, right? Because that's what's forming in the transition state. I'm forming a CO bond. Now let's think about the charges here for a moment. Carbon is going from +1 to 0 formal charge. What's its delta charge in the transition state? If you said delta plus, you're correct. How about the oxygen? Well, the oxygen's going from 0 formal charge to a +1 formal charge. So therefore, the oxygen also has a delta positive charge on it. So it's kind of a weird transition state where I have a carbon and an oxygen both having the same positive, delta positive charge, which means that it's a fairly high energy transition state. Okay. So now we come over here, and now I'm going to break the oxygen-hydrogen bond, and I'm going to form an H+. So this oxygen-hydrogen bond breaks, and the pair of electrons then goes to this oxygen, leaving an H+, and maybe I should write the H+ over here on this side. So it's a product along with then our substitution product, our alcohol. What would the transition state here look like? Well, the transition state here would be breaking that oxygen-hydrogen bond. So that's going to be a partial bond. The hydrogen is on its way from 0 formal charge to +1, so it's delta plus. The oxygen is on its way from +1 to no formal charge. So therefore, now in this case, this transition state, the hydrogen and the oxygen are delta positive, and I'm breaking the OH bond. Okay, so this is how we would get the mechanism for a neutral nucleophile reacting with either a tertiary halide or a secondary halide. And that means that there's now two intermediates in the reaction, the carbocation and the oxonium ion. So when you reacted this tertiary butyl bromide with water, your first intermediate is the carbocation, your second intermediate is the oxonium ion, and then you get your final substitution product, which this should be the OH, and this should be an H plus and a Br minus. Okay. So that slide went with the earlier reactions. Now, if you think you have writing the mechanism of an SN1 reaction down with a neutral nucleophile, how about we try this one? Let's take this secondary halide and react with a neutral weak nucleophile of an alcohol. The rules are such that the weak nucleophiles can only undergo SN1, so fortunately secondary carbocations can form. They're not as stable as tertiaries, but they can form. So this reaction would go by an SN1 mechanism, and now in this case it's going to form, we're going to add an OCH3 group to the carbocation, and then again have an H plus Cl minus as our other product. So given that reaction, can you write the three steps for this SN1 mechanism. If you want, stop the video, try it, and then come back and see if you were right. If not, then just go straight to watching me write the mechanism. So in the first step of the mechanism then, I'm going to break the carbon-chlorine bond to form my secondary carbocation and my Cl-. And I suppose I should probably write the transition state. Okay, now in the second step of the mechanism, what's going to happen? That carbocation is now going to react with the oxygen of the CH3OH. So the oxygen is going to come in and react with the carbocation. What am I doing? Should put my lone parent on the oxygen, so there's that. And now, what would my transition state for this reaction look like? It would look like this. So my C of the carbocation is going from +1 to no formal charge, therefore it's partial charge in the transition state's delta plus. Got a partial bond between forming the oxygen-carbon bond. Then the oxygen's going from 0 formal charge to +1, therefore it has a delta plus charge. So this is the structure of my transition state. And then the final step in the mechanism is to then take that oxonium ion and now break the oxygen-hydrogen bond. I'm just going to write the transition state here. To form my final product, which is actually an ether functional group. My oxygen now gets its lone pairs back, and I ended up producing H+, which would have reacted with the Cl- up there to make HCl. Okay, so that's how I would have written the 3 steps of this mechanism. And we'll practice drawing mechanisms more in class on Wednesday. So the key step in the formation of, or in the SN1 reaction is the formation of the carbocation. So if you can't form a carbocation, you're not going to undergo SN1. So what we find is that tertiary halides react faster in the SN1 than secondaries, and primaries don't react because they don't form a stable carbocation. Don't worry about the benzylic and the allylic carbocation or their reactions and their carbocations yet, because we'll talk about those next semester. Okay, so tertiary reacts faster than secondary, which reacts faster than primary because primary doesn't form a carbocation and therefore doesn't undergo SN1. Okay, so in parallel to what we've talked about SN2 so far, we've talked about kinetics, mechanism and what your textbook calls how the substrate reacts, whether it's tertiary, secondary, or primary, which one reacts the fastest. And what you'll see is you've got a complementary nature of SN2, SN1. What do I mean by that? Primaries undergo the fastest SN2s, but they don't undergo SN1, but that's okay because they undergo SN2s. Tertiaries weren't able to undergo SN2 because of the steric hindrance around the carbon, but that's okay because they can form the most stable carbocations, and so therefore they can undergo SN1. Secondaries are like the problem childs because they're in between, and so they can react as either SN1 or SN2, and they're the ones that we're going to have to probably just say they react SN2 when they're reacting with negatively charged nucleophiles, and when they react with weak nucleophiles, the neutral ones like water and alcohol, they have no choice. They're just going to be reacting SN1. And we'll summarize all of those kinds of reactions on Friday. Okay, so all this says, the big red crosses says no primary carbocation, no SN1. So last thing we have to talk about, and it is the last thing, is what happens with chiral molecules. We saw that chiral alkyl halides underwent inversion of configuration in an SN2 reaction, and therefore the R configuration became S, or vice versa, but an optically active product gave us an optically active alkyl halide in SN2 gave us an optically active product. Does that happen in SN1? If I was betting at this point, I'd say no, because everything's been opposite for SN1 and SN2. And you'd be right, because what happens is when you react an optically active chiral alcohol in an SN1 reaction, what you end up with is a racemic mixture of enantiomers. So therefore, what happens is when you react an optically active alkyl halide, if the mechanism is SN1, you get a racemic mixture which is not optically active. It doesn't rotate plane polarized light. So how would that happen? Well, in the first step of the mechanism, I'm going to break my carbon-bromine bond and I'm going to form my carbocation. What's the hybridization of that carbon and the carbocation? And remember, we made the analogy to radicals a few minutes ago. So if you said sp2, you're correct. So here's my sp2 hybridized carbon. I've kind of written it on its side. Here's my p orbital. In the radical, the p orbital had 1 electron. Well, I just took that electron away to make it a plus charge, so what's in this p orbital? Nothing. It's empty, but it's still there. So these three groups are then trigonal planar. So now I have a nucleophile. And so now my nucleophile, if I'm looking at now the orbital picture of this, my nucleophile is going to take its lone pair of electrons in an orbital and it's going to overlap it with one of these two lobes of the p orbital, because that's how we form bonds, right? We overlap orbitals. So the nucleophile could add to the right lobe here, or that nucleophile could add to the left lobe. And which one is it going to prefer? Well, there's nothing stopping it from adding to either side, so 50% of the time it's going to add from the right, 50% of the time it's going to add from the left. And what's that going to do? Well, when it adds to the right, I'm going to end up with this molecule. Now, these color groups, this dark blue, green, and red, are different than the nucleophile's light blue. When the nucleophile added to the right lobe or to the left lobe, what happened? I get this molecule, and what are these two molecules? They're mirror images. Since there's no preference for adding to either the left or the right lobe, I'm going to get then 50% of one enantiomer, 50% of the other enantiomer, therefore I'm going to get a racemic mixture of the two products. So an SN1 reaction takes an alkyl halide that's optically active and makes it optically inactive by forming the racemic mixture. Okay, and so that's the last part that we talked about with SN2s are what happens when you take a chiral alkyl halide and react it together. Or react it in SN2, you got an optically active product with inversion. For SN1, you get a racemic mixture. Okay, so here's an example. If I reacted R2-bromobutane with cyanide, what I would end up doing is forming the carbocation. The cyanide could react to either the left or the right lobes, empty lobes, which are truly empty this time because I didn't show them, but they're there. And so then I would get the S enantiomer with inversion of configuration 50% of the time. I would get the R enantiomer, which would come about from, in essence, retention of that configuration 50% of the time. And so therefore I would make a racemic mixture. So here's what we've learned about unimolecular substitution reactions. Number one, that the mechanism is at least 2 steps. It's 2 steps when it's a negatively charged nucleophile reacting. It's 3 steps when it's a neutral nucleophile or a weak nucleophile. But the 2 steps are cleavage of the carbon-halogen bond to give you the carbocation, and then the attack of the nucleophile on the carbocation to form either the substitution product if it's negatively charged nucleophile, or to form the oxonium ion, and then the loss of H plus to give me the final product. But it's at least a 2-step mechanism. The kinetics is unimolecular. The rate determining step is always the formation of the carbocation intermediate. And so therefore the rate is only dependent on the concentration of the alkyl halide. The rate of the reaction is also dependent on the stability of the carbocation intermediate. And we could go back, which I'm not going to do right now because your heads probably would explode, but we could go back and talk about how Hammond's postulate and how the Arrhenius equation comes into play. But basically, the more stable the carbocation, the faster the reaction. So tertiaries react fastest, then secondaries and primaries, since they don't form carbocations, they don't undergo an SN1 mechanism. They only undergo SN2. And last, when you react an optically active halide, you get a racemic mixture, and therefore you get a product that is not optically active because it's a racemic mixture of the two enantiomers. And that's because we go through an sp2 hybridized carbocation intermediate. Okay. So that's everything you wanted to know, or, well, you have to, about SN1. So what we'll do for Wednesday's lecture then in class is, if there's any questions about any of these aspects of the mechanism, we'll get some practice writing the mechanisms, and then I may have a few questions for you.